Today we're going to look at rational exponents. And so just as we can write numbers in multiple formats, so if we have a decimal, we could write it as an improper fraction or a mixed number. We can also write radical expressions in different forms. And so keep in mind too, if we're looking at rational exponents, otherwise fraction exponents, we've always in the last several years tended to go towards improper fractions. So we're always going to be going something like 5/4 rather than writing it as a mixed number. And you're going to see why that's important when we do our converting on these problems. So when we have a radical expression where we have an index and our radicand, so again, index being the n that I have in that first box, we can rewrite that as a rational exponent. The numerator of that exponent is going to be whatever exponent is on the radicand, so the number that's inside the radical, and our index is going to go in the denominator of the function. So as we're looking at these problems, you're also going to want to keep in mind some of our rules for exponents. So a reminder, when we're multiplying terms that have the same base but different exponents, so x to the a times x to the b, we add our exponents. Okay. If we have an expression that already has an exponent raised to another exponent, like in our second example, we're going to multiply our exponents. This one's probably new. If we have a negative exponent like x to the negative a, then we can write that really as a fraction. So we have, for example, if we had x to the negative 2, we would write that as 1 over x squared. So it tells us to take basically the reciprocal of that expression, but keep the expression with the positive exponent still in that denominator. And then when we're dividing, we are going to subtract our exponents. So as long as, again, the base is the same, you can subtract the exponents like we did in the example. And we'll see a few problems that, kind of mix and match these rules. With our rational exponents, another thing to remember is, how we can just convert just any random expression sitting underneath a radical of whatever index. So if we have square root of x, again, our implied index is 2. We could write that as a to the 1/2. Cube root of a, we could write as a to the 1/3. Fourth root of a, we could write as a to the 1/4. And so no matter what our index is, if we call that index n, we could always write this as 1 over n as a rational exponent, So let's start looking at some examples. So in our first set, we're going to write each expression in exponential form. So in other words, we want to write these as a base raised to an exponent, and our exponent is probably going to be a rational value. So in our first one, we have 4th root of a cubed. So again, if we have 4th root of anything, we saw that in our example, that means we're going to have an exponent of 1/4 applied to whatever was already in the radicand. So we're going to have a cubed raised to the 1/4. But we don't want to leave it like that, and so we can use our exponent rule, which says we can multiply those two exponents. So this is really going to come out to a raised to the 3/4. And 3 times 1/4 would just give us 3/4. Okay, square root of b cubed, same thing. So square root, I know that's the same as raising whatever the radicand is to the 1/2 exponent. But then use your power rule, multiply your exponents. So we'll have b raised to the 3/2. Okay, now 3 is getting a little bit more complicated just because we have a 2 out in front. So whatever we do, we're going to keep that 2 sitting in front of our expression and kind of copy that down. So we want to attack cube root of b squared. So again, b squared raised to the 1/3 power. So again, none of those powers affect that 2 that we had as our coefficient. And so we can rewrite b squared raised to the 1/3 power is really b to the 2/3 power. And so with these three problems, you'll notice I've kind of taken an extra step in there. I don't really need to write the index as a radical exponent every single time. I can kind of combine steps and just write my whole expression all at one go. So in number 4, I have the 4th root of x cubed. Well, if I go back to that first rule that we wrote down at the top, or up at the top, Whatever exponent is with the radicand goes in the numerator. Our index goes in the denominator. That's it. But you can always lean back into your exponent rules to simplify things out if you get stuck at any point. Alrighty, so number 5. The way I'm going to approach this is, let's put that 1/5 exponent to represent our 5th root, or our index of 5. Let's put that on every single term and then see what comes out when we simplify it. Actually, let me shrink that down a bit. So we're going to have 32 raised to the 1/5 power, x to the 10 raised to the 1/5 power, and y cubed raised to the 1/5 power. And so if I think of applying that 1/5 power to each factor that was underneath the radical, well, 32 to the 1/5, and again, you can plug this into your calculator if you need to, but think about what kind of factors does 32 have? So off in the margin, let's see, 32, I know that's 8 times 4, but 8 divides out into 2 times 2 times 2. 4 divides out into 2 times 2. Wait a second. I have 5 2's as the factors of 32. So that means the 5th root of 32 is just 2. Okay, x to the 10 raised to the 1/5. If I multiply those exponents, what's 10 times 1/5? Well, it's really just 10 divided by 5, aka 2. And then y cubed raised to the 1/5. I don't have any fancy simplifying I can do, but I can multiply 3 times 1/5, which would give me y to the 3/5. And that would be my final answer. Alrighty, a few more. Let's kind of go backwards and still use some of our power rules, our exponent rules, to do some simplifying. So again, we want to write these eventually in exponential form, but if we're given the problems already in exponential form, then really all we're trying to do is simplify these out. So again, if we have the same base but different exponents, what was our rule again to do with those exponents? It was the first one on our list. So all we need to do is add our exponents. So piece of cake with this one, we have 1/7 plus 4/7. We have the same denominator. We can just go ahead and add them and get 5/7. But we run into a problem with number 7. So in number 7, a to the 1/3 times a to the 5/6. If I'm going to add those exponents, my problem is to add 2 rational expressions, to add 2 fractions, I need to have the same denominator. So how could I make that 1/3 have the same denominator as the 5/6? Yeah, multiply everything times 2, kind of like what we just did in the rationalization examples. So I'm going to multiply the numerator and denominator by a 2. So that's going to turn this into a to the 2/6 times a to the 5/6. And now I can add my expressions. So I'm going to have a to the 7/6. And again, we're leaving this in exponential form, so I do not want to write this as a radical, and I'm going to leave it as an improper fraction, because again, if I need to take an answer and change it back over to radical form, then I'm going to need to know specifically what the numerator and denominators are. There's no point in changing that over to a decimal or a mixed number. Okay, number 8, 5 to the 1/2 times 5 to the 1/2. So same denominators, same base with the 5. But what's 1/2 times or plus 1/2? Well, that's just 1. And do you ever see us write things with an exponent of 1? Hardly ever. The most simplified version is just 5. Keep in mind, 1/2 of exponent, that's really square root. So square root of 5 times square root of 5, still going to get us to a 5. Alrighty, what's our rule again if we have a power raised to a power? And all we're going to do is multiply. So we need to multiply 1/4 times 2/3. But neat thing on this, I can actually simplify my fractions. So 2 goes into 4 2 times. And so really, if we're just going to multiply our fractions, again, don't forget you multiply straight across. And so multiplying the numerators, we have 1 times, well, just 1, because we simplified out that 2. And the denominator, we have 2 times 3, or 6. So this is just x to the 1/6. Okay, and then our last example, we have 4x to the 7/8. We have 2x to the 1/8. So our division rule, instead of adding our exponents, we're going to subtract our exponents. And so I do like to divide these up into 2 problems. So I'm kind of looking at my variables and I'm looking at my numbers. So with my numbers, I know 4 divided by 2, well, that just simplifies out to a 2. X to the 7/8 divided by x to the 1/8, I know I'm going to have to subtract. So my thought process is 7/8 minus 1/8. But wait a second. That just comes out to 6/8. And can't I reduce that fraction? So that's really 2 times x to the 3/4. Completely reduced version, no fraction left whatsoever. Okay, now would be a good time to go ahead and pause the video. You have 2 pieces to your U-try problems. So now that we've done our first set of examples, try out the U-try 18 through 22, and then check out how you did in the completed version. Okay, let's check out our second version. So in all of these practice problems that we just did, we changed everything into exponential form. Everything was represented, or our final answers were all represented in exponential form. Well, in our next set, we're going to go backwards. So given whatever expression it is, we need to change it so everything's written with a radical instead. So let's check them out. So first set of examples, x to the 1/2. So again, don't forget the denominator of that rational exponent is your index. The numerator is whatever exponent stays with your radicand. So in 11, that means we'd have a square root from the 2, and we'd have a 1 on our x. But again, we don't typically write these with this format. We have an implied 2 as our index, even if anything's not written. We don't usually write an exponent of 1, so we would write this as square root of x. In number 12, again, same pattern. So our index is the denominator, so this is going to be a cube root problem. And then the numerator stays with the radicand. I don't have anything else I can simplify in this one. He's done. Boom. Alrighty. Number 13, 16 to the 1/2. So I'm throwing a number in here, so we're probably going to have a number as our final answer. But 1/2 exponent really means to do what? I'm going to take the square root. Wait a second. Square root of 16? Well, that just simplifies out to 4. We don't even need a radical in this one. He totally simplifies out. So what do you think's going on with number 14? Let's see. So I have a fraction. I'm going to deal with that in a little bit. And I'm noticing 25 over 36. Anything special about those numbers? Those are both on our perfect square list, aren't they? And that 1/2 exponent, what does that really mean? Take the perfect square root. So if I think about taking the square root of 25 over 36, wait a second. When we were simplifying these out before, now I'm perfectly fine to write these as 2 separate radicals, but square root of 25 is just 5, and square root of 36 is just 6. It's another one where everything just totally simplifies out, which is always nice. Alrighty, number 15. So 15 is starting to look a little different. We have a negative exponent, and it's a fraction. So I have 2 things that I need to do. So anytime we have a negative exponent, that tells me automatically I'm using a fraction in this problem. I always write that part first. So I really have 1 over 27 raised to the 1/3. And so now let's deal with the radical. So again, 1/3 exponent really means what kind of radical? So this is really 1 over cube root of 27. Except, wait a second, 27, isn't that a perfect cube root? That's 3 times 3 times 3. So when I simplify this one out, hey, it's done. No more radical. So actually trying to put this into radical form gave us a much more simpler answer. 1/3 is a lot less complicated than 27 raised to the negative 1/3. All right, number 16. So we have x to the 3/5, y to the 32/5. So I'm noticing both of these have 5 in the denominator of the fraction. So that means both of these have the same index. So I can put both of these expressions underneath a 5th root. Keep the numerator though. So x to the 3rd, y to the 32. And so we always want to see if we can simplify any further. And I can't do anything with 5th root of x cubed, but 5th root of y to the 32. Do I have any groups of 5 y's that I can take out? Well, yeah, if I have y to the 32, well, 5 is a multiple of 30. So I could really do y to the 5th, which would simplify out to y to the 5th. I could do 6 of these, 3, 4, 5, 6, and I'd have a leftover 2 y's. Because keep in mind, if we go back to our basic exponent rules, I could add all my exponents. 5 plus 5 plus 5 plus 5 plus 5 plus 5 gets me up to the 30, plus those 2 extra to get to the 32. And so if I simplify this out, I'm looking at, let's see, 1, 2, 3, 4, 5, 6 of those that I can simplify out. So y to the 6th. Nothing else simplifies out. So I have to keep the y cubed and I have to keep the y squared underneath the radicand. So 5th root of x cubed y squared. And again, notice I'm being very careful to keep any exponents from those coefficients completely separate from my index so I can clearly read what I'm writing out. Alrighty, last problem. So 16 and 9 both raised to the 1/2 exponent, but what does the 1/2 exponent really mean? Yeah, it really means square root. Okay, so square root of 16 and square root of 9. Wait a second. Those simplify out really nicely. That's just 4 over 3. All done. So hardest one out of all of these was 16. But again, as soon as we wrote it in radical form, we used the same techniques that we did in lesson 7.3 when we were simplifying out those radicals. So actually, lesson 7.1 when we were simplifying those out. So I'm going to go ahead and stop the video. You are now ready to try the 23 through 26 U-try examples. But again, all of the U-try examples will be in the completed notes. So try them out first and then check to see how you did. If you have any questions, let me know through Zoom before you try out your practice and definitely before you try out your mini quiz. If I don't talk to you, have a great rest of the day.